So an example we can look at here is one in which you're dealing with oxygen binding to hemoglobin. Now, it's possible to have a number of different health conditions that change how oxygen binds to your hemoglobin, and this largely can be predicted by looking at the energetics of the binding process. So the idea here is if you have a normal or standard blood cell, binding reduces the energy of hemoglobin by some particular amount. If you compare that to a patient that has a uh, non-standard cellular configuration such as sickle cell, instead of binding to oxygen, reducing the energy of hemoglobin by this amount, the amount actually differs. Now, for the human body, it is possible to get a rough temperature value. Say you can get a energetic temperature value by taking that temperature in Kelvin and multiplying it by the Boltzmann constant. And what you might want to figure out is, of the two patient types, which one might absorb the least amount of oxygen, or which one has a harder time binding oxygen to it. Now, to deal with this, you need to deal with the energies of these processes. Now, when you're dealing with this, you have to actually look at where your energy is measured from. So basically, at the start, you have some energy level, which is non-bound hemoglobin. And what you're told here is when you are dealing with uh, normal cells, or the standard cells, reducing or binding an oxygen molecule here brings this energy down by a particular amount. And the same is true for the other one. Now, if you take a look at this, what you will find is you've been provided with these two numbers. Each one is not particularly the energy of our system, it's just how much this energy has been brought down by. So when you're dealing with these, if you're asked to find the probability of each of these events occurring, what you're going to want to ask yourself is, of these two energies, which are relative to the same standard level, which one is lower? And what you will find is that the red one here is lower. It's dropped from the black line more than the blue line. So this one is lower. Make it red. Or this one here has a lower energy. And lower energies naturally mean they will be more likely, just based on how the math works. Now, with that being said, in order to deal with our relative probabilities, we need to know how much different these two energies are. So I'm going to move this one up because it doesn't drop as far. It has a higher energy. So to use the Boltzmann probabilities, what you need to know is, in between these two lines here, you need to know what delta E is. Right? You need to know what the change in energy is. Now, when you're dealing with these delta E's, they're always energy 2 minus energy 1. So basically, what we're going to want to do to make delta E positive is we're going to want to call this blue one here state number 2, and this red one here state number 1. This energy, even though the number is smaller, is closer to our original point and therefore has a higher energy. Right? This whole energy goes up this way than our original one. Right? So if you call this state 2 and this one state 1, you can find your change in energy by simply taking E2 minus E1. And if you take a look at the differences in energy here, what you'll get is a positive quantity of 0. What are we dealing with here? 0.12 times 10 to the negative 20. The blue one actually has a higher energy than the red one because it's come down from this top reference one less. Now, once you have that, what you can do here is you can find the relative probabilities. So you compare the probability of the second type of binding to the probability of the red first type of binding. This is always equal to the exponential of negative, the change in energy, divided by the Boltzmann constant times the temperature, which we have up at the top. I'll switch the screen up at the moment, but what we know to be 4.2 times 10 to the negative 21. Now, you can literally calculate this out, uh, evaluate the numerator of the exponent first, then apply the exponent to it. What you'll get here is 0.75. And what this is saying is the probability of this second type of binding is only 75% as is likely as the probability of this first type of binding. In other words, you're a fair bit more likely to have oxygen binding occur in this normal or wild type than you are in this changed type. And you can do so literally by looking at how much energy is different between these two bound systems.